Welcome back. As we continue our discussion of finite sums, we start to notice some patterns, and because there are some patterns or the sums that we use a lot, we have some formulas for those sums that we know. So what you can see here is we have the sum for the first n integers, the first n squares, or the first n cubes. So when you're dealing with just k, k squared, or k cubed. And I'm going to prove to you why this is the formula. I'm going to just use the first one. So we are going to show that the sum of the first n integers is n times n plus 1, that quantity divided by 2. So we want to prove this is a true statement. And the formula tells us that we can find the sum of any quantity n, any n quantity of integers. So sometimes when we're examining sums, it's helpful for us to look at what the terms would look like. So I'm going to do two things here. I'm going to list out what I think those terms would be, and I'm also going to calculate what that sum is by the formula. And I'm going to do this for my first 4 terms, okay? So we're going to calculate the first 4 terms and their sum. So if I were to list out my terms here, if I were to do, say, the sum from k equals 1 to 4 of k, that would give me 1 plus 2 plus 3 plus 4. And what that equals is 10. And if I were to calculate this for my nth term being 4, that would be 4 times 4 plus 1 over 2. Which gives me 4 times 5, which is 20 over 2, and that simplifies to 10. So we see that this works, this is true, for n being equal to 4. So what we're going to do to prove this, we've verified it by actual addition for 4 terms, and we could do this over and over again, say let n be 10, let n be 20, but that's a lot of busy work. So to prove this, I'm going to list out my terms. Let me scroll down here. So this will be my proof. Okay, so to prove this, I'm going to list out my sum. And what I would have would be 1 plus 2 plus 3 plus 4, and so on, such that at a certain point, I'm just adding up to my nth term. So that would be the sum of the terms forward. Now, if I looked at adding those terms in the reverse order, so I started with the last term, and I'm going to end with my first term. I would have, well, my last term would be n, and the term that comes before n would be n minus 1, and the term that comes before that would be n minus 2, and before that we would have n minus 3, all the way down to where we're adding up to, eventually we have 1. So let me just pause and clean this up here. So I rewrote this with a little more space so we can see that together. So what we want to remember is that this first row is the sum of all of my terms counting forward, right? And the bottom row is the exact same sum, just written in the reverse order. Okay, so that's n terms backwards. And the top was n terms forwards. So if I took these two and added them together and said, let's find the sum of both of these, I would have two sums. And if I look at adding this first piece here, that would be 1 plus n. This next term, I would have n plus 1. My next term, 3 plus n minus 2. Again, I have n plus 1. Four plus n minus 3. Again, I have n plus 1. All the way down to my last pair, that would give me n plus 1. Okay, so I've calculated this, and now I have that two sums are all of these n plus 1 values. And how many n plus 1 values do I have? So this is n plus 1 n times. So we have n times n plus 1 here. And I added it up twice, right? I had two sums. So this n times n plus 1 is equal to double the sum. So in order to get that back to the value it should be, we're going to take it and divide by 2. And so now we have proved that the sum of the first n integers, k, from 1 to n, is n times n plus 1, all of that divided by 2. And so that just lets us know that this is a true formula and we can use it. These other two, the sum of the first n squares and the sum of the first n cubes, those can be proved by mathematical induction, but I'm just going to give them to you and let you know that you can use them.